sections. Leverson Award 23 for outstanding scientific contributions. He completed a PhD in geology from West Virginia University. And today he's going to talk about integrated geothermal resource assessment, a techno-economic analysis, a case study from Presidio County of the Trans-Pecos region of Texas. Chit, take it away.
Thank you so much. Just one question. Are the slides shared on Zoom? Yeah. Okay, that's great. Thank you, everyone. And thanks for inviting me. Geothermal is hot right now. There's a lot of exploration going on in different parts of the world, including US, New Zealand, Turkey, and many different places, using new concepts, new technologies, including drilling and completion technologies. And the great thing about geothermal is that it's a commodity, it's a resource. So you can use it for power generation, you can use it for different kinds of direct use, like heating or cooling, or even absorption chillers for the data centers. So that's a great thing. And it can provide the base load energy to the grid. As the grid is becoming more vulnerable with more and more demands coming from the AI centers, data centers, and growing industry and population, it is important to keep it reliable. And that's where geothermal has a really good value. And at the same time, if we adopt this energy, there's a possibility of saving greenhouse gases, that decarbonizing the grid. That's another positive factor of using the geothermal resources. Another option is that another good thing about geothermal is modular, it's highly modularized. You can use it for different purposes, whether small or big, depending on the local demand. Not that everywhere we need electricity generation. We can use it for district heating or greenhouse gases, things like that. So there are a lot of different areas geothermal could be used, or even in conjunction with solar or wind, has been exemplified in some of the projects. So that's a really great thing. So there's a lot of momentum going on right now. And so considering this, Bureau and Ken Wishnu, we established a geothermal working group and basically a hot rock geothermal research consortium that is funded by the industry. We started it last year. Start with the funding from 3 companies: Shell, Chesapeake, and Schlumberger, or SLB. And we are working on different projects that has to do with EGS, like enhanced geothermal systems, closed loops, as well as hydrothermal systems. So this group is more like a technology agnostic, and should I say, science biased. And so, we have quite a few of our research scientists and professors who are working with us from the department as well as from the Bureau, and working on the geology, geophysics, reservoir engineering, techno-economics, and many different other areas. So this is mainly industry-funded consortium. This finds and fills the science, the technology gap in the geothermal, and how we can use it for outreach and policy making going forward. So these are some of the areas that we are currently focusing on, and that includes characterization, including geologic data, geophysical data, then your high resolution temperature, data acquisition from the wells, machine learning for play fairway mapping, and there are development options like faults and fracture mechanics, reservoir engineering, and then all comes down to techno-economics. Should I use it for power generation? Does it make economic sense? What's the LCOE looks like? What's the break-even price or the payback period? And use it for either power generation or for direct use. So, and this group, or the broader geothermal group, we are of course looking at sedimentary rocks, that's in Texas, but also non-sedimentary rocks that can include igneous rocks like basalt or even granite, that kind of rocks in anywhere, and it's not just specific to Texas. So, and these are some of the projects that we have been doing for last a couple of years, and some of these have been done in the overall in a geothermal group, not necessarily to the hot rock. And so, working with different startup companies like Sage Geosystems, which is a Houston-based startup, and working on different DoD-funded projects in Corpus Christi, then El Paso, like Fort Bliss, where he completed the study very recently, looking into different kinds of geothermal potential, like hot, dry rocks into the Precambrian basement, trying to achieve a temperature like 150, 200 Celsius for power generation. And of course, looking at the energy storage as well. Recently, we have a project from the DOE and Los Alamos on doing geothermal and lithium together, like techno-economics of your lithium extraction from the hot geothermal brines, and how does the techno-economic picture look like? Is it profitable, and can we do both? What are the complementary technologies we should be using for this? One of the important parts is that the techno-economics, and I will tell more about this a little later. There are so many technologies right now. So many startup companies are coming up every other day. Things like closed loop system, single well closed loop, or a horizontal well closed loop, or multilateral closed loop, energy storage, mechanical energy storage, then thermal energy storage. So many different options are there now. But how do you know which one is better? And that depends on the techno-economics in a given area, depending on the local geology and the local demand. That's a very important factor here. So that's an important area we do work on. Interestingly, when we look at the heat flow database, the temperature data from the US, there are different sources. But when you compare the data structure to the international structure, there was a vast difference. It was not conforming to the international standard that we see in many other countries. So there was a project we did for the project Inner Space last year, and that is basically harmonizing, homogenizing the entire US heat flow data into a format that one can use to compare with other countries and other places. And for example, that includes, let's say we have this temperature data. Where does the data come from? Is it a measured data or is it estimated data? What's the quality of the data? These things were not there before. So now we have added more granularity into the heat flow database, and this is very useful. And going forward, we will see more and more of these activities happening. We have now built a lab for thermal conductivity diffusivity measurements. We recognize it's a critical thing for different kinds of rocks. So we can measure the conductivity and diffusivity at somewhat high temperature and pressure as well. And we are working with Nicola Tisato from the department for different high pressure temperature rock physics experiments. So there are many of these things that we are doing. And before us, there's been decades worth of work that has happened at BEG from 70s, and there were so many reports and have been published on the Gulf Coast geothermal, tight sandstone reservoirs, and the Frio reservoirs on the Gulf Coast. So many work has been done over time. We are leveraging those studies, building on them, and getting ready for tomorrow. And so in the last, 2 years ago, with the funding from the Mitchell Foundation, we produced a report that quite a few of us from BEG were involved in writing several chapters in the future of geothermal in Texas. That's a report publicly available, and it has geology, geophysics, then policy, engineering, a lot of different other factors there. So that could be used as well. So now, before I talk about the actual case study, let's talk about these things first, because this has a large implication of what we really need to consider. So a lot of innovations going on in the geothermal space right now. And then that is including improvements of this conventional hydrothermal system, like for example, the geopressure geothermal. back in the days, Bureau was involved in drilling the Pleasant Bayou test wells on the Gulf Coast near Houston. And they're primarily targeting the overpressure Frio formation. And the idea was to produce the hot fluid and to generate power from that. And so, and for that, what we really need a good reservoir with high porosity and permeability and good connectivity, and of course high temperature, right? So that is good. So that was a thing people have used in many areas, and of course in the West Coast, near Nevada and Utah, those areas is also the hydrothermal system. You have hot springs nearby, and you have this high porosity and permeability mainly, and you have this formation fluid coming out. That's great. But then there's another challenge with that, is that when you start looking to the actual data, the fluid production from many of these reservoirs on the Gulf Coast, then what you see that for this actual power generation, we need like 20,000, 40,000 barrels of water production per day. We don't see that from these wells. So the question is then, how do we keep this system running after the initial water production has happened? So then comes, can you inject cold water, the injection well, and producing hot water from the production well, like injector producer pair. So there is that aspect of the hydrothermal geothermal. Then comes the EGS. That's basically where we are involves the fracturing of the tight hot rocks, and they're circulating this fluid through that and producing that. There are many areas where it has been implemented for power generation and direct use, for direct heating in the Northeast, the Appalachian Basin, also in Utah, Ford site, and other areas where it has been implemented. Recently, Farvo Energy, where they're drilling these horizontal wells, and then drilling and perfing with the help of propans to keep these fractures open, so the fluid can continue to flow through those fracture systems. That's another great example of that. And then comes the closed loop system. That's more advanced and more newer things. And this is where we drill this more engineered system where you don't there's no connection directly with the rocks. Actually, it's build a system that can be like a U-tube system, drilling two wells connecting them like a U-tube, and it can be a multilateral well. It can be one single hole that can have one annulus and circulating the fluid within the entire casing. So that's kind of system that is also becoming popular. And there are quite a few companies like Ever, then your Sage, and Geosystems, they are working on these things, including field demonstrations for power generation and direct use. But then there are challenges. So some of the areas, this becomes a very attractive option. For example, in areas where hydraulic fracturing or stimulation is banned, there it could be very useful in those areas. And then, or if you know the rocks like salt has a high thermal conductivity, but then it doesn't make sense to EGS or hydrothermal systems there. And if you do a closed loop system, then that can make sense. So it depends on the situations where you are. So for the EGS and AGS or closed loop system, these have definitely have a lot of popularity increased in the last couple of years. But then this new phenomena that people are talking about now, the energy storage, the mechanical energy storage or thermal energy storage, that has increased the momentum quite a bit, and that is helping us to realize or democratize, let me put it that way, geothermal energy into the market, because many of these things are pretty lofty, like closed loop systems, things like it takes a lot of capital for drilling, engineering, and maintaining that. But with this, you can actually combine with the solar or the wind. And recently, there are companies like Sage who are working on a system for energy storage in a vertical well, creating the fracture and then doing the energy storage. So that was the overview of this. So now what I'm going to do, I'll talk about the case study in that area, in the Presidio of Southwest Texas. So This project was funded by the Presidio Municipal Development District, and the KNU Vision was the PI of the project. And so the main objective of the project was to explore the geothermal resources in that area that is near Southwest Texas. And it's near in the Trans-Pecos region, located near the Rio Grande Rift. And there have been, over the years, there have been so many studies have taken place. People have looked at the geochemistry, the fluid samples and things like that, and heat flow measurements. So we find out that in this overall area, around this area, near the Rio Grande Rift, we do see high heat flow, and then also high geothermal gradient at places. That's how we started. So this looks like it's promising based on the background literature information. And then, but then what you look at this, then what's the demand of this, where we can use the geothermal? So what we notice that there is one electricity transmission line, there's outcrop transmission line, a single line coming from Marfa to Presidio. So, so if we and there are some other facilities they have it, like they have this molten salt battery system, then they have a solar plant. So there are some other plants that are available for the electricity generation. But then the idea of geothermal is that if we can plug it, connect with the grid, it can provide a base load energy for 24/7. That's an important part. So, so you want to do the techno-economics to justify the feasibility. Does it make sense? Either for power generation, and if it is not economic, can I use it for direct use, for, let's say, agriculture, or let's say food processing, or data centers? So there are different kind of opportunities that's possible here. So when we started looking into this, then there are a lot of challenges that we encountered, and many of us at Bureau, they worked on this project. So from different aspects, from the geology, geophysics, engineering, techno-economics. So we found the foundational challenge was to deal with the extreme lack of subsurface data in this area, and compared to other places that are used like Gulf Coast or Permian, where you have thousands and millions of those wells with the well logs or seismic. We don't have those things here, and many of the oil and gas wells that have been drilled here, most of them have been found to be dry and abandoned. Just recently, a couple of years ago, there was a company that drilled 2 wells in the Austin Chalk equivalent in northern part of the county, and it's a vertical frac, but just for the shale exploration. We don't have much knowledge about those either. This area has a complex geology. We're dealing with sedimentary rocks, non-sedimentary rocks like your granite, rhyolites, and different kinds of your volcanics. Here, like basalt and many other types of rocks. And it underwent so many different kinds of tectonic movement, faulting, intrusions, volcanism, and that makes the subsurface very complex. That was very challenging. But then over the years, there have been quite a bit of outcrop studies have taken place. In the 50s, 60s, or 70s, a lot of outcrop studies have taken place. Even today, there are some studies going on in these areas, like Big Bend and those areas, Chinati Mountains and those areas. And we can find these kind of challenges in many other parts of the US. That is geologically complex and data lean in that way. So this is the data we started working with. So we procured a high-resolution gravity data to start exploring at a regional scale, looking at the surface geology maps, then looking at the temperature data from the BHT data, the bottom hole temperature from the wells. Then we had well logs from few wells, and we had one core. We had one well with the core from the Ellenberger or El Paso group. So, and as I said, there have been a lot of outcrop studies have taken place. We started taking the help of the literature. And this is a geologic map sheet that was produced in 2000s. And this is near the Big Bend area. And so this is kind of not much legible, so I just zoomed in here. And we see these kind of Paleozoic, Mesozoic, and Tertiary rocks exposed on the surface. That includes your different kinds of carbonates, as well as your different kinds of carbonates, limestone, dolomites. And then you have this Precambrian granitic rocks, rhyolites, and then you have this tertiary volcanics exposed in many places. And here is an interesting feature called Solitario. That's basically a caldera that's considered one of the largest. It's a laccolith. It's considered one of the largest laccoliths in the world. And then many of these rock sequences are exposed there. So use this information and looked at the well logs, the drilling mud logs. Then we kind of come up with a very simplified lithostratigraphy that can work, that we can start, that we can use for our subsurface analysis. And so we're starting with this Precambrian basement rocks, like granite, rhyolites. The basement is heterogeneous here. It's not just granite. And then we got this Bliss sandstones here, on the Van Horn sandstone, the Bliss sandstones, right near the basement. And then we got this El Paso, the Ellenberger group of the carbonates. We got others like a Fusselman, Montoya. Those groups are also present here. And so mainly the Paleozoic, Mesozoic section is mostly dominated by the carbonates with some siliciclastic mud rocks. And then in the Tertiary, that was a time for your basin range, the faulting, the extensional faulting, then volcanism. A lot of areas of volcanoes happened. And we see those extrusions like the basaltic basalts and tuffs, and some of the areas we got these intrusives as well. Again, this is not to scale, but this gives an idea. Starting with these granitic rocks, then you have this mostly carbonate-dominated sedimentary section, and then you have these volcanic rocks at the top. That's the kind of idea. So now I'll talk about the regional picture here. So we started looking at the publicly available gravity data from the USGS and looking into what is available there. Oh, and so what you're finding out, these different gravity highs and the gravity lows in the basins, and finding different kinds of basin, like Valentine Basin, Marfa Basin, and then this thing called balsams, which are basically quaternary sediment fill, like Presidio balsam. These are basically graben systems that have been filled with the basin fill, with quaternary sediments, alluvium deposits. Then the Redford balsam. There have been this is a nomenclature that is kind of common in that area, like El Paso, Hueco Mountains, the Trans-Pecos. This nomenclature is common. So we started looking at the USGS data, and then what do we know from our previous experience? That this data is really great, extensive, publicly available for screening. But when it comes to actually a project, drilling, or let's say local site characterization, that data is not always very helpful. And so and that's why we ended up using proprietary industry data that are higher resolution. So here is so what I'm doing here, showing you the data from the publicly available data on the left and this high resolution data on the right. So one of the main differences between these two is that this public data that we have, it has a coarse grid. It has a large station spacing, then higher flight altitude of the data that's collecting the magnetic data, or in this case, gravity on the ground. But on the high resolution data, we have a much finer station spacing, much tighter grid spacing, so you get to see a lot more details. So if I look at this, one of the things we notice, the first thing that is you can notice near the Valentine Basin here, mostly like a semicircular feature here, but when you looked into the high resolution data, then it looks like there are some lineaments, there are some structures that are present in that area. And back in 70s, this Valentine Basin was considered as, it has a graben that is present in the Cenozoic system, and we can identify that on this high resolution gravity data. So and then other areas definitely we do see here, for example, like near the Big Bend, near the Cincinnati Mountains area, we do this area underwent through your basin range faulting. The Rio Grande Rift Zone goes through here. So these mountains here, so going through that, and also on the volcanism, there can be some concealed faults that you could not identify with the public gravity data, but we could identify with this kind of data. So now what we did, we started digging into more and applied different processing approaches like total horizontal derivative, tilt derivative, looking into these edges basically, and helps us identify those features. And these are well-known methods that are used in the potential field geophysics domain. And so use this to identify those boundaries, the basin boundaries, the faults that are present. Most of these faults are extensional faults along northwest, southeast. There are some transform faults that we see along east-west as well. So now that we know this, so then the next question was, because this becomes very important for EGS systems, where is the basement depth? How can I estimate that? Because as I said, there are no seismic, we did not have any seismic data, and there are only a few wells, only three wells we found that penetrated the basement, and there is a large variation. So these two wells that you are seeing here, the BH1, BH2, they penetrated the basement at around 8,000 to 9,000 feet, but then this one was really, really deep, like more than 5 or 6 kilometers. So we had only a few areas, but we're looking at the entire county scale. We had to use different methods to estimate the basement top depth from this gravity data. So there are different methods that are used. So we basically did the inversion of the gravity data, the high resolution gravity data, and constrained with the basement with these three wells, BH1, 2, and 3, where we had those to constrain the basement depth. Now, one of the things to keep in mind, the gravity data, magnetic data, these are highly non-unique. They can have so many interpretations, and that's a very important thing to keep in mind. There are many different non-unique solutions with this data, and therefore it's really important to validate the data with actual well drilling, or even if outcrop information, things like that. We did a lot of iterations to reduce the error between the observed and the synthetic gravity to come up with this basement depth. And if you look at that, what we find the Presidio Balsam is around 5 to 6 kilometers deep. The basement, the Precambrian basement is deep there. Then of course the Big Bend area is most exposed. It's pretty shallow basement there. Valentine Basin is also deep compared to the other basins like Marfa basins. So this is going to be helpful. Now what we did, as I said, we looked at many of these geologic map sheets, the outcrop data, and the literature that's available out there. But then we did not find that many in the subsurface, actually. Most of the studies were done outcrop. So what we did then, we used this high resolution gravity data to basically forward model and generate these different kinds of basin the geologic cross sections along different profiles, like north-south profile or east-west profiles. And so here is one of the profiles from starting from the Big Bend area going to the north. And as you're doing this, we took different assumptions, and many of those assumptions were based on the outcrop information. For example, the faults and what could be the fault deep of that. 50-degree deep or 70 degrees deep, we use outcrop information to guide that. And of course, we assume if I see a fault deep of 50 degrees on the outcrop, it should continue in that way. But that may or may not happen everywhere. There can be change in the dip. So, and then the other part was that if we have, what we're trying to do, we have this observed gravity in the dash, and then you have the calculated gravity with this forward model, trying to minimize the error between them, trying to match as much as possible. But while doing so, we're also trying to use some of the constraints for outcrops, and some of the areas could be better defined. for example, these forms and the geometries of these intrusives, right? And if we had closer or higher resolution data, more than this, or maybe a site-specific data, right? And then we used one of the wells, BH2, that penetrated the basement to confirm this. And so then we do another cross section here that is going mostly along east-west. This is the Valentine Basin, bounded by these faults on both sides. It's a graben system, and then we use different densities of these rocks, basement, Paleozoic sediment, tertiary volcanics, to prepare these cross sections. As a result of that, we have somewhat improved understanding of the complexity of the subsurface. So this was a geologic cross-section from the gravity data that was published in 1980s, mostly along east-west. And this also, we have a profile along east-west from the Presidio Basin to the Marfa Basin. And it helped me understand, so new data, new technology helped understanding these basin structures, then this continuity of different kinds of layers that we can image on this gravity data. For example, is intrusives or this tertiary volcanics. So you have somewhat improved understanding from those, and you can delineate the structures better than what we had done before. So now let's talk about the temperature. There are different sources of temperature data in the US. One of the most well-known is the SMU temperature data. And this data contains both measured data as well as estimated data. It is publicly available. And so it's a compilation of temperature data, estimated or measured heat flow. So a lot of this information are there. So this is the map that was produced back in 2011, and the warm color shows the high temperature. So this is where we are. And as I said, we recently completed another study in this area near El Paso. This is part of the same Rio Grande rift system. So this is, and there are many different public sources of data these days. The SMU data is there. Then there is the Stanford temperature model that was released last year. And then the project Inner Space, they have also geomap versions of the temperature as well. Now, each of these data, even though some of them use many common data sources, there are quite a bit of challenges and gaps if you come to the site scale. And we found many different limitations of these data sets. And for example, these data sets, I mean, we know, I mean, some of the many of this depend on the interpolation of that. And when you look into many areas, especially in this area, we found that these publicly available maps, they did not consider the deep boreholes. So most of those wells they used were shallow wells. We did not find any deep well information used in those studies. And there are many other challenges with this. What kind of correction method was used to estimate the temperature, like Harrison's correction, other methods, that does change this picture. And in fact, what we have found out, one of our colleagues, Bisset Young, she presented a paper at the recent GRC conference and shows, depending on what temperature corrections method we use, it can change the techno-economics quite a bit. That means a marginally viable project can be economically viable if we use different kinds of processing tools and for this temperature. So that's why we use this information, the SMU data, and looked at temperature distribution at 5.5 kilometers, and then looked at our own data set, right? And so we had around 100 wells in this area in the Presidio County. This is the well distributions. There's a hot springs here called Chinati Hot Springs. Many of those wells are along this Rio Grande Rift zone, and there are some wells with the temperature data in the interior. When you plot this data, the temperature versus depth, and so we see kind of moderate geothermal gradient, like 29, 30 Celsius per kilometer. And this data that you see, these blue samples, we have applied Harrison's corrections to that. The reason is that when you get this bottom hole temperature data, like from the wells, they don't represent the true or the equilibrium temperature, because you have used drilling mud. Drilling mud somewhat disturbs the system. So the temperature you get is cooler. The temperature is reported. The reported BHT at a deeper depth is cooler than the true subsurface temperature. And therefore, there have been different corrections have been proposed, have been used, like Harrison's corrections, Foster's corrections, different methods, different parameters. We use this one, that's a well-known and mostly based on the depth. But then there are other corrections depending on the compaction of sediment as well. There are other methods that's present. So what we see here, in many of these power generation projects, we look at a temperature of 150 or 200 Celsius for power generation, for a sustained Techno-Economics. And if we look at that, what you'll see that here, the 150 Celsius, we achieve around 5 kilometer depth, right? So keep that in mind, 150 Celsius at 5 kilometer. If I start looking into the border region, this area, then if I plot that data, temperature versus depth, it is somewhat different. The geothermal gradient is much higher, which is around 47 or even 50 Celsius per kilometer in this area. And that is due because of this, the Rio Grande Reef, the thinning of the crust, and higher heat flow in many of these wells. So the border, and here, if you remember, if I look at the 150 Celsius, then I see this coming around 2.5 kilometers. So I have a much shallower depth where I encountered this higher temperature. Now that impacts the geology. But before I talk about that, let's look at a little bit closer here of this temperature depth plot, because we see this phenomenon in many different areas. So we have quite a few samples from around 500 meters. And then we have some deep samples here. And so we can construct many different geothermal gradients, different kind of slopes, right? And that we can use in the Techno-Economic projections. The problem with that, in many of these BHT samples we see at a shallower depth has this high temperature gradient, I should say widely varying geothermal gradient. And there could be multiple different reasons. It could be like if you are doing the temperature measurements during warmer months of the year, so ambient temperature is also high, if the shallow temperature is affected by that and the shallow depth. If there is a groundwater flow in the shallow subsurface, that can also disturb these temperature measurements at the shallow subsurface. There's a Rio Grande River there. Or if you have a shallow thermal anomaly. Many areas you got these magmas of volcanic areas where that can also disturb the temperature gradient. If you got a nearby volcanoes, that happen in many areas. So we do see these things in many areas in the Basin and Range province. Why does this thing matter? Because for many of the hydrothermal systems in those areas, if it is like 1 kilometer or depth or 2 kilometer depth wells, then probably it doesn't matter that much because I'm still in that high temperature regime, right? But for the deeper systems, for let's say 3 or 5 kilometer depth, then what we see there is a different gradient there basically. And we need to know because the deeper subsurface is cooler than the shallower subsurface. That's what I mean to say, and that can completely change the Techno-Economics and of the operations of this geothermal plants. So, just to get a simplified version of those stratigraphies here. Here is the border region, and here's the interior region. What we see here, this is much shallower. Here we have a higher heat flow. We see 150 Celsius at 2.5 kilometer, which is mostly near the basement. And this depth that is here, it is based on the actual borehole data that penetrated the basement. Most in the shallow basement, we encountered this high temperature. But for here, the interior region, we have to go around 4 to 5 kilometer depth, and we'll still be in the Ellenberger carbonates to achieve that 150 Celsius. And the basement is pretty deep there, and there's a lower heat flow. That kind of gives you this depth estimates of this. We can consider isotherm temperature and see how these depths are varying for 150 Celsius, 200 Celsius, and that can help a lot. We had a core from this area. So we worked with Kiki Wang, and she helped us a lot to describe these fracture systems. And we had only core from the Ellenberger section and finding different kinds of fracture styles there, the break-shaded fractures, or even tectonic-related fractures. And many of these fractures were actually mineralized. And so we use this information to construct a fracture abundance log from this core and use this information for the techno-economics. What's the fracture intensity there, and use this information. So now this is like a summary of this information that was used in the economics. Like we had this mainly 3 types of reservoirs: Precambrian, Paleozoic, Mesozoic, and Tertiary, looking into the depth of those formations, thicknesses, the porosity, and the thermal conductivity. So we measure some of this thermal conductivity at the lab, and then we also use some of the analog formations to get the thermal conductivity values. So if you look at this, the border and the interior region, their rock properties are pretty different. So now comes the techno-economics part, and this is a very important part that we consider. So now that we have done the subsurface analysis, we know the formation thickness, the temperature, the porosity, and those are the thermal conductivity. So now we went on to the resource assessment, quantify the resource that is available there. We use 2 approaches. First approach is the USGS type approach, heat in place. Just like a resource in place, oil in place, or gas in place, there is also heat in place estimate. And it's called heap array analysis. And it is popularized from the 70s. It has been modified over time. It's a simplistic volume-based approach. What do we need? We need the area, thickness, then the porosity of the reservoir, then the temperature of the reservoir, and how much is on the rejection temperature and the heat capacity. So if we have all this information, multiply them, I can get an heat in place estimates. Then, but then we know many of these properties have highly uncertain, right? So people also do Monte Carlo simulations, give different ranges to better estimate those. So here is an example for the heap array analysis for the interior region, showing that how much electricity you can produce from this per unit area. So this is a preliminary approach, but then that tells the resource that's there. That's primarily dependent on the geologic factors, all right? But it does not take into account the well completions, like what kind of technologies I can use. Like, am I going to use EGS system, like stimulating the reservoir, or let's say closed loop systems, or use it for different kinds of use, like direct use. It does not look into those, so that we can actually, transform the resource to the utilization, right? Different project scenarios. So there are some tools out there. One of them is called GeoFire's tool. It's developed by NREL, the National Renewable Energy Lab, and we do a lot of programming, and there are some desktop-based versions as well. Collaborated with them, Malcolm Ross, who primarily worked on the techno-economics, who worked with Conrad Bakers from NREL, and also did a lot of coding inside this object-oriented programming. So it's a lot more detailed, comprehensive economic analysis that includes a sales price model as well. And you need a lot of input variables, like 100, 150 input variables that includes your different kinds of reservoir models. And also you can use different kinds of completions geometry as well for different kinds of systems, like EGS or AGA, like closed loop systems. And what you get out of that if I put a plan for power generation, how much power it's going to generate? Is it going to be 5 megawatt or 10 megawatt of electricity? Or is it going to be economic? Measure the net present value, then the LCOE, the levelized cost of electricity, like the cost of producing the electricity, is it cheaper or more expensive than selling the electricity to the grid? So we can get those ideas from this modeling. So here, is a quick heat-in-place estimates what you see in this diagram that shows that the basement reservoir, the Precambrian basement reservoirs, have this higher heat production capacity and the electricity production capacity. This has been used, but then, as I said, that we have to transform into either electricity or direct use. So the heat-in-place is important, but you have to transform in something that is more tangible and you can use directly into the projects. That's why we now we use this GeoFires tool for the economic analysis. So we made some assumptions. So first, for the power generation, we assume that the selling price is 15 cents per kilowatt hour. It's higher than the grid price, which is 6 cents. And the reason it was done, because many areas have this military bases who can afford to pay for the premium. And there are communities that can afford to pay for the premiums. If you use the higher sell price, that's actually a good thing. In cases, but at least to see if this project is going to be economic or not at the long term. With the inflation rate of 2% and no subsidies was used in this analysis. So what we found out, so there are multiple scenarios we generated, 4 scenarios for power generation. All of most, it's like a cascaded scenario, like EGS system, then the one close to EVOR style system. And these are the reservoirs that are targeted, all of the Precambrian basement rocks. What we find out from these cascaded scenarios, first we went with the aspirational temperature, like we are going to reach 200, 240 Celsius, right? That was the target. And if we go with that, then, and 2 injector, 2 producers in an EGS setting, we can get electricity producing up to 21 megawatt. That is good. And generally, we're looking for 5 or 10 megawatt, 21 megawatt. It's decent. But if we look at the LCOE, the break-even price is around 3 to 4 cents per kilowatt hour. This is important because even if we look at the actual selling, the selling price of the electricity to the grid, which is 6 cents, it is economic if we can do within 3 to 4 cents per kilowatt hour. So we don't need to consider 15 cents at the time. It is economic. And then, of course, at the time, our net present value becomes higher, and the return becomes higher in those cases. But in that case, the depth of the drilling is around 4 to 5 kilometers. So I'm talking about 4 wells, 2 injectors, 2 producers, all of them drill up to 5-kilometer depth into the Precambrian basement. That can add a lot of capex and opex as well, right? And but then we may or may not be able to reach that target. What if we lower the target, like instead of 240, if we do a 200 Celsius, if we do 200 Celsius, then still into the basement. And in this case, the drilling depth was around 3 to 4 kilometers. Still 2 injectors, 2 producers. And in that case, what happens? I'm producing less electricity, and my LCO is becoming slightly higher, but still less than 6 cents. That's my selling. That's the actual selling price. But then the model assumes 15 cents, but which is still good actually. And we have a higher net present NPV and higher IRR. So that is still profitable over the long term. And these project scenarios include 20 to 30 years for the lifespan of the project. We looked into one of the 2 scenarios for closed loop system. These are like multilateral systems that connected like YouTube basically. We considered those, and one of them was in the border area. And if we do that, of course, you can look at the much higher capex because drilling those wells and horizontals and completely keeping close to it takes more, higher capital. And then in terms of production, generating the electricity, it was around 6 megawatts, half than EGS, and the LCOE became higher. Now I'm coming closer to the model assumption that was 15 cents. So now I'm 13 cents here, right? So then my NPV is lower, the rate of return is lower. But again, this is a site-specific thing. This is all of them models were in the border region. Now we moved on the interior region for one of the cases, and we targeted 170, 175 Celsius. If we do that, then and then as I said, 175 Celsius, we have to go at least even 5 kilometers there, based on the cooler temperature gradient in the interior region, right? And so in that case, the LCO is become higher, NP, the net present value is negative at the time, not making money at that time. So it is depending on the technology and the location, and what's the selling price of this. So we do see these things from these models. We then looked into the direct use. Many areas, direct use is becoming more popular for heating or cooling. Many areas in Europe, they use for district heating. And so here, there are many different options we used for the agricultural processing, then your greenhouse gas, then connecting with a direct air capture from the CO2, and as well as absorption chiller for data centers. What we found out from these scenarios, the food processing is one of the important factors so that you can make profit. And targeting again, it's an EGS type well, so doing a 240 Celsius target, we can have a high NPV, and the payback would be within 2 years. That's a pretty attractive project. The next one could be even absorption chiller. But there are many data centers, AI centers that are being built. We need to cool them continuously. In those cases, we can use geothermal for direct cooling of those systems. And in that case, the NPV and return is still much higher. So let me come to the conclusions. So there's a lot of value of the geothermal. It's a value proposition of geothermal. Because if I look into this area now, so we got this one electric transmission line. There are many other retired plants like wind turbines that have been retired, some other facilities there which is not operational. So we can use geothermal to provide electricity to the grid, make it more reliable and less vulnerable. We have some existing facility like some solar facility and the salt battery. But the battery, as you know, it takes time for charging and discharging. So geothermal can be used as a base load to keep it online 24/7. That's a good use of that. And a large portion of this county is within the economic development zone, like this area near Presidio, and this area is quite a bit of this area is in the EDZ, as we call it. So there could be some incentives for new project investments, and also there's opportunity for cross-border business. This area, we have this Ozinawa city, a town in Mexico, which has a higher population than Presidio. So it can be used for even connecting the grid, providing electricity there, or even transporting the food that is being produced, the crop that is produced in Presidio to the other borders, like a near-shoring type of thing. That could be, and there is a train rail line that is going to be operational by next summer 2025. So, and there's a lot of great things about geothermal, a lot of positive impacts, and it can also helpful to reduce the greenhouse gas emissions as a part of this. But there are assumptions into that as well. So let me conclude this. So we found out this study area has a substantial undeveloped resources. The border region has high geothermal gradient compared to the interior region. It's a complex geology, and so we recommend for any project development, collect high resolution geophysical data, drill slim holes, collect temperature logs, fluid samples, and we do find opportunities for both power generation and direct use. We considered both EGS and the closed loop systems. What we find out, at least from our models, that the EGS systems in these cases, if we do this in the Precambrian basement, targeting 200 Celsius or more, that can have higher net NPV and a short payback period compared to the other kind of systems. We have not considered energy storage. We only considered EGS and AGS. And direct use, there are other options for absorption chiller, agriculture processing that can be profitable as well. And this was funded by the Presidio Municipal Development District. And thanks to the companies for donating the data, providing the data, and the companies for the software. And thanks to you all.
Thank you, Jit, for this very interesting talk. If you're online, if you have questions, please raise your hand or type your questions in. We can open time for questions here in the room as well. We already have a question online. Enzo, would you like to ask the question, or we just read it? You can just probably go ahead and read it. Many thanks for the presentation. Would an analysis like this allow decision makers to move to an actual final decision investment, development, or an exploration project? Sunk costs need to be devised. How much would be if so?
That's a thank you for this question, Enzo. I mean, for this kind, as I said, that these projects need to go beyond the heat in place assessment. We need to consider different kind of techno-economic scenarios in the local market conditions, and that's really important. So doing these different kind of scenarios helps a company to decide where they should invest. For example, if I am finding out the border region has a really high geothermal gradient, but my electric transmission line is far from there, it doesn't help me. So you have to come closer to the electricity transmission line so I can transfer the electricity quicker, without constructing a newer grid. So these kind of scenario modelings are actually pretty helpful.
Any other questions in the room? Yeah.
Thank you, Jim. Thank you. I love geothermal. The idea of getting energy out of heat is awesome. And it's always seemed like, not quite there. And you showed us that it's a multifaceted problem. I've always had the impression that the stickiest spot was the generation from the use of fluid that wasn't really where usually we use steam. Want steam to drive things. If you have less than steam, then the mechanics of the extractor fall off. Is that right? And who's doing what? I mean, to improve the design of engines away from steam engines to warm water engine. Is that a key thing?
That's a very good question, and I would say that this is an important consideration, and many traditional geothermal projects like West Coast, like Nevada, Utah, California, they have been affected by this. It's a steam-based system or a hot water-based systems, mainly for the hydrothermal systems. And but with these new technologies that is involving, like your multilateral drilling, plugging and perfing, and extracting the hot water, or basically circulating the water, like inject cold water and circulating the hot water continuously, that has somewhat reduced the concern. If we are using, let's say, closed loop systems or other kind of technologies, then that does not affect that much. But again, those challenges are there. If it's steam versus hot water, then it can have it can impact the scaling over time. So there's one practical considerations is there. Scaling of the let's say that if you are exposed to the rocks, and then what happens, the mineralization basically. Yeah. Mm-hmm.
Thank you, Jit, for this excellent presentation. I got a question for the specific of your project, because you are counting on the fracture. The best gradients are actually in the basement. That is, you are counting fractures to have good permeability, and it looked like from the core, most of the fractures are already sealed. I mean, they are close fracture, so you need to be frack, and then how much fracking you need to be doing? Is it like a 20-year, 30 years project? So because in the oil industry, you frack a well and there is a life for the well and you make money. But in this case, if you had two injector, two producer, so it's planned to continue to refract the rock continuously so you can flow the water, because otherwise you have to abandon the project to make it economic. So you need to count and put that on the calculation also, that the fracking, the continuous fracking that you need to be doing during this time. So, and is there any statistic also in somewhere else in the US that they have done this?
So there are some of these projects that are continuing, many recent projects like the Farvo project, that's going on, where they release some of the production data, right, from this fractured, the stimulated fracture systems from the basement, right? And so yes, there is an option that we should consider, or not option, it's a requirement to add some development where the infill well drilling over time because of this decline of the production. One of the things is that in this area, I showed an example. It has a nice score, so many different kinds of fracture styles and that. But then it's already highly naturally fractured. So the problem is EGS. I mean, first of all, the efficacy of stimulation in the already existing fractured zone, and the second part is that if you have a fast flow path for the heat to this, if you have some short circuiting, basically, that you may lose, you may have a rapid decline of your heat over time. So the new EGS systems will need to consider those and design it accordingly.
And before we transition the room here, there's a quick question on what is the radiogenic heat production of the granite?
That's a very good question. So this is one of our limitations in the study. We did not include the radiogenic heat production from these granites into our model. What we're doing now, we're actually we are looking into other things like Curie depth estimates, other things. We have a consideration to add the radiogenic heat production, but not as a part of this study we have completed.
So you almost preempted my question at the very end by saying that you did not look into thermal storage, but I'm still asking you the question, and you just have to make it up, I guess. Isn't thermal storage the low-hanging fruit here? You mentioned abandoned wind production. That seems kind of strange to me. With thermal storage, which has much lower requirements in terms of making it feasible, lower depth, cheaper infrastructure operations. There's many things that speak for thermal storage. Wouldn't that be the first thing to go after, and then maybe combine that with heat extraction? What's your
I would say
to that, without having looked into the detail?
I mean, so there's a lot of projects that are brewing up in this area. The company is interested into doing the geothermal exploration drilling in the Presidio County now. And this could be for your direct use projects or even for power generation. But I somewhat agree with you that for this, the energy storage, whether mechanical thermal energy storage is an option to make it realize basically the potential of geothermal before going and drilling a 5-kilometer deep well and spending money on that. So this is an option that is more feasible that one should look into, because there's already a battery system there. There's molten salt battery system. The solar plant is there, so you can connect with those. So that's definitely an option. People where the project developers should be looking into that. But we did not do this because our tools didn't have for the energy storage Techno-Economics, but we're actually working on now. So I plan to do that in the future. But we did not model that scenario. It is a stepping stone. That's the right word. Yeah.
Any other questions in the room? There's a comment online by Sam Clarin. Great presentation, Shivaji. TEAs are vital in pushing geothermal forward. One comment is that next steps should consider social barriers to such projects. Many face resistance operating in sensitive areas such as Big Bend and Rio Grande. Transparency and communication are crucial in conjunction with TEAs in getting projects started.
Yeah. That's a good comment, and I agreed with that. I mean, many areas of fracking could have some legal issues and whatnot, right? In California and many other states, right? So then the good thing about geothermal is modularity, whether it's closed loop or EGS. You can use those involved, but does not involve fracking, or definitely more outreach, more transparency. And one of the good things about Presidio is that this was the first county, probably in Texas, or maybe even the country, but I might be wrong on that side, where this molten salt battery, the NAS facility was constructed back in 2010 to generate power, and there have been a somewhat interest in different kinds of renewable resources in that area, so it could be possible.
All right, let's thank Jit again for this interesting talk. Next week is AGU week, so we won't have a presentation, but after that we have our final talk of the semester by Molly Turco, and another structural geology talk, and we hope you can make that. Thank you.